Good morning, everyone. Today we will be looking at a new topic. We'll be looking at the design of bevel gears. Bevel gears, as we know, are used to transmit motion in uh, in the shafts which are having intersecting axes. So we'll look how do we design it. The basic theme remains same. We for the design purpose, that is the strength design purpose, we convert the bevel gear into its equivalent spur gear and then use the theory of spur gear design for the design of the gear tooth. But there are other aspects which are unique to the bevel gears, which we'll cover. Let's first see the how the bevel gears operate. So this is an animation of the bevel gears. So as you can see here that the axis of the yellow gear is vertical, whereas the other gear is horizontal. In this case, they are perpendicular, which is the most common configuration, but that need not be always the case. So you can have the gears with different uh, angle between their axes. Another thing to be observed is that this gear tooth, they lie on a conical surface. So if you extend the top surface of the gear tooth, they will form a conical surface. And similarly, on the back side, that is on this side, uh, also you have a conical surface which is getting formed. And another thing to be observed is that the profile of the tooth, if you look at the black colored gear, the back side of the teeth you can see that is larger in size, whereas if you move towards the front of the gear, you find that the tooth size is different. That means the tooth profile means although it is an involute profile, but the size of tooth at the back side is different than that at the front side. So that makes some complications in the strength design of of the bevel gears. We'll see how do we tackle that particular aspect. Now let's move into what are the different types or classification of bevel gears, which I want you to read through the textbooks. I will not be covering that part. So we have seen this. There are different types of bevel gears. What we saw in the animation, those were the straight bevel gears. So the gears what we saw were straight bevel gears where the gear tooth are straight. There are other types of bevel gears which are known as spiral bevel gears and hypoid bevel gears. The spiral bevel gear as well as the hypoid bevel gear, they have the advantage similar to that of the helical gears that the engagement happens gradually. As a result, you can use them for more higher power transmission with less amount of noise and vibrations. Depending on the geometry, that is the angle which this conical shape of the bevel gear has, and also what is the summation of angle between the two gears, there are different names given to the types of gears which are well explained in the textbook. So I want you to read through that. So it is a nomenclature. So different types of nomenclatures are used to define the different types of gears. So just be aware of what is meaning of that. For our calculation purpose or the design purpose, we require to understand certain notations. So the first thing that is to be noted is that the tooth profile, if you draw, extend the pitch lines of the bevel gear tooth. So this is the bevel gear tooth. So if I extend the pitch line of this bevel gear tooth, it will all the gear tooths. So that is, if I draw the pitch lines through all the gear tooth, they will all converge into one point, and these lines will form a conical surface. So this particular conical surface, which is given here, so this is known as pitch cone. Similarly, if you extend the backside of the gear tooth, they too will converge into another conical surface, and that surface is known as back cone. So these are two terminologies. We use the back cone for some purpose for converting the bevel gear into its equivalent spur gear. We'll come to that shortly. The other important things to be noted, as I said earlier, that the gear tooth dimensions are different at different locations. So if I consider the large end of the tooth, you have got a different addendum, you have different dedendum, you have got a different pitch circle diameter. And if you come as you move towards the smaller end, you will find that the pitch circle diameter will keep on reducing, the addendum will keep on reducing, dedendum will keep on reducing, and so on. So the least values are at the apex or towards the front side of the gear tooth on the pitch cone side. So if you have to specify the dimensions of the gear, that is what is its pitch circle diameter, what is its module, you have to specify at which location it is. So the convention is that you specify the bevel gear dimensions at its large end. So when I say that the pitch circle diameter of bevel gear is 100 millimeters, that means the pitch circle diameter is at the large end. So this D which we'll use in our calculation, so that is always specified at the large end of the gear. And D divided by number of teeth is the module. So the module is also specified at the large end. So note that unlike the other types of gear where module is constant throughout, here depending on the location, the module value will keep on changing. So point to be noted is that all dimensions of bevel gear are given at the large end. Another important thing, or not important thing, but from design point of view, when we are converting this bevel gear into its equivalent spur gear, we use the radius of that equivalent spur gear as that of the slant height of the back cone. So if you note here, so this is the back cone which is formed by the backside surface, and this back cone surface is perpendicular to the front cone surface. So this is the front cone or the pitch cone line, and this is the back cone line. So these two lines are perpendicular to each other. If you develop, so you imagine this as a cone, and if you develop this conical surface, you will get uh, circular shape, and the radius of that circle would be equal to the slant height of the cone. So the when you develop this particular back cone, you get a circle, and that circle radius is the pitch circle diameter, pitch circle radius of the virtual gear. So we use that gear or that profile what we obtain when you develop the back cone of the gear as the virtual gear or formative gear. So formative spur gear has got a radius which is equal to the slant height of the back cone. So I'll repeat once more that in the bevel gears, the dimensions, that is the pitch circle diameter module, they keep on changing depending on the location. So they are specified at one location, that is the large end. And second thing to be noted is that when we are doing the design calculations later on, we'll be converting the bevel gear into its equivalent formative gear. And for that purpose, we use the radius of formative gear equal to the slant height of the back cone. So these are the two things to be noted. Why we use this particular radius, that explanation is given in the textbook. So you have to just go through that. I'm not covering it here. Okay, so now that we are talking about the spur gear, about the equivalent spur gear or the formative gear, here uh, we have got a gear which is having a larger diameter. However, we want the formative gear to have the same involute profile as that of the original bevel gear. So this particular formative gear will have same module as that of the original bevel gear. So as a result, since we are maintaining the module same, the number of teeth on this virtual gear would be different. So let's establish the relation between the number of teeth on the virtual gear versus the number of teeth on the actual gear. This is similar to what we did in the helical gears. So there also, since we are taking a different plane on which we are cutting the helical gear teeth, we get different diameter, and we maintain the same module because module is the one which governs the involute profile. So by maintaining the module same, we get the tooth profile uh, similar to that of the original gear tooth. However, since the diameters are different, by keeping module same, we are changing the number of teeth. So same thing is happening here. So let's establish the relation between the module. So module can be written in two ways. So one way is in terms of the original dimensions, that is the diameter, pitch circle diameter at the large end divided by number of teeth. So that is d by z, where d is the pitch circle diameter at the large end, and the same module will has to be maintained for the formative gear. So for the formative gear, the radius is 2 times rb, and the number of teeth are z dash. So this z dash is what we are trying to establish. So what remains to be done is to write rb in terms of d. So it's a simple trigonometry. So can somebody tell what is the relation between rb and d? Just look at this figure. So rb is this dimension. This is rb, and d is this dimension. So can somebody tell what is the relation between rb and capital D? I'll repeat the question. In order to determine the virtual number of teeth, we have to eliminate this rb and d. They are not independent. So rb depends on capital D. So what is that relation? By simple trigonometry, you can find out. Okay, here, okay, one particular thing I missed, which may not lead. The pitch cone, the angle of the pitch cone is also an important design parameter. So that is denoted by gamma. So the pitch cone angle, that is the half apex angle of the pitch cone, is termed as gamma. So this gamma is required in order to develop the give the relation between capital D and RB. So RB can be written in terms of D and gamma.
2 times RB cos gamma.
Sorry, 2 times.
RB cos gamma.
Yeah, that's right. So you have the right angle triangle here. So where this angle would be equal to gamma, and this particular height is equal to t by 2. So we have the relationship that uh, RB would be equal to AB divided by cos of gamma. AB is this particular height, and AB is nothing but capital D by 2 divided by cos of gamma. So we get the relation as RB equal to D divided by 2 cos gamma. So if we substitute that in the above equation, you get D by Z equal to 2 times D by 2 cos gamma divided by Z dash. So here the D gets cancelled, 2 gets cancelled, and we get the relationship Z dash equal to Z divided by cos of gamma. So this is the relation that we will use similar to the helical gears. So equivalent number of teeth on the formative gear for bevel gear will be given by this particular number. So when we are using the beam strength calculation, we require the number of teeth for Lewis form factor to determine the Lewis form factor. So there you have to use this virtual number of teeth. And again, you don't have to round around this number. You have to maintain this number as it is. Okay, so this is something basic information about the geometric dimensions that we need to know. I think I might have missed something more. So another dimension that we require is this width of the gear and the slant height of the pitch cone A naught. It also will require in some other calculations. We'll come to that later. So these are the things, these are the dimensions which are important. The addendum and dedendum are there, but we don't require them in our calculation purpose. Yeah, I think I have covered all the dimensions there. Okay, so we have some quiz coming up here. So let me put. Okay, so pretty simple question. So I just mentioned that the dimensions are always measured at the large end. So large end is the answer, which most of you have given. Okay, so remember that bevel gear dimensions are always given at the large end. Let me stop here. Okay, so this is the second question. What is the radius of formative gear? Okay, so here the correct answer is 2. That is the back cone slant height is or slant distance is used. So on the bevel gear, you have, since we have seen this already, but I'm just writing for the sake, since I see significant of them have given first answer. So this is your bevel gear tooth. So if you draw the pitch line towards the front side, so this is known as the pitch cone. And if you extend the back side, you get what is known as the back cone. So this is the back cone that we are talking about. And formative gear is formed by developing the backside of this, or the developing the back cone side. So you get the tooth which are the backside. Okay, so the correct answer is 2, not the first one. Okay, now most of the times you have the two intersecting axes perpendicular to each other. So that is common configuration where you many times in many of the machine components you'll find that two axes are intersecting at right angles to each other. So the pitch cone angle, the gamma, what we discussed in the previous slide, so it is an important design parameter. So for this particular configuration, the pitch cone angles of the pinion, so the smaller one is the pinion and the larger one is the gear. So the pitch cone angle, this particular symbol is known is capital gamma, and this is the small gamma. So both are gammas. But for conventionally, the gear that is a large gear pitch cone angle is capital gamma, and the other one is small gamma. Now on the right hand side, you see some relation which is written here. So tan of gamma is given as Zp by Zg, number of teeth on pinion divided by number of teeth on gear. So can somebody tell how we can arrive at this expression? So tan gamma is a geometric expression, and on the right hand side we have number of teeth. So how they are related? So I'll rub off the markings so that you can see the figure clearly. So my question is, how do we derive this equation? Tan gamma equal to Zp divided by Zg.
Tan
dp by
gamma
dt
is
is constant.
Okay, Vikas, can you tell?
Yes, sir. So tan gamma is equals to dp by dg, and dp is equals to mzp.
Mzp, and this is Mzg.
mzg.
That's right. Good. Thanks, Vikas. I think Prasad was also saying the same thing.
yes sir, yes sir.
Okay, and similarly, you can get the expression for tan of capital gamma, that is for the gear, is a reverse expression. Okay, so that is pretty simple. So some quiz is coming up. Okay, so here the answer is, let's see what majority of you are saying. Oh, you got both. Okay, so that means I need to ask you why. So which is the somebody who is saying the answer is true, that this configuration tan gamma is Zp by Zg is true for all bevel gear configurations. So can somebody tell why option 1 is correct? So let's look at this particular figure. So what expression we developed here, tan gamma equal to Zp by Zg, is it true for any of the Bevel gear configuration? So how we develop this is we consider tan of gamma equal to this height divided by this distance. So this is dp by 2 and this is dg by 2. So will it be true for any bevel gear configuration? What I mean by the bevel gear configuration is what if the axes are not perpendicular to each other, will this hold true? The most common configuration is the axes being perpendicular to each other. If they are not perpendicular to each other, that means one gear is as shown here horizontal and the other gear is smaller one, so it is engaging. So this is the second gear whose axis is not perpendicular, so in between that, let's say the angle is 60 degree. That configuration is possible. So note that this particular equation that we developed is true only if there is a right triangle which is being formed here. If this particular line OB is inclined, then this particular expression will not be holding true. So the correct answer is no. So that just remember that you cannot blindly use this expression for any bevel gear configuration. Only when axes are perpendicular you can use this. Okay. So any questions or doubts at this stage?
No doubt, sir.
Yeah, thank you. Okay, now we'll move to the force analysis for the bevel gear. So let's understand the net force which is acting on the bevel gear. So we are having the total force in this particular figure. It may look very complicated at the beginning, but the single force, if you bring down the total force acting on the bevel gear, it is this force which is inclined in space. It is perpendicular to the gear tooth. At the same time, it is having in the case of the spur gears, we are having the pressure angle concept. So in the similar fashion, this particular force is inclined with respect to the horizontal plane for this the gear, the configuration which I have drawn. The horizontal plane with respect to uh, it will make an angle which is the pressure angle. So this force which is the bevel gear involute profile will also have a pressure angle. So the pressure angle is the inclination of this red line with respect to the line CD, and also it is inclined because of the pitch cone angle. So this angle gamma, it also makes the inclination of this particular case of this particular force. So what hatch plane you see here, so I'm talking about this plane. The blue colored plane which I have drawn here. So this plane is cutting the is perpendicular to the pitch cone. So that is more clear. So this plane is nothing but this blue plane. Plane ABCD, which is a blue plane, is perpendicular to pitch cone. So this is the pitch cone. If you draw a surface or a plane which is perpendicular to pitch cone passing through the gear tooth, then that is the plane in which the net force lies in. So the net force lies in this particular plane. So that red force, if you look at, it lies in this particular plane, but it is not perpendicular to this conical surface. It is inclined by an angle which is corresponding to the pressure angle of the plane. So this particular force, that is the force BD, so from B to D, can be resolved into two forces. One force which is tangent to the gear tooth, so that is force CD. So the CD is nothing but the tangential force, and the other component, this is known as the sliding force. So the net force can be resolved into a tangential force and a sliding force. And the sliding force, which is this particular component, can be resolved into two components. One is the axial force component and another is the radial force component. So these are the three different components which we are familiar with. So thrust component, the axial component, and the tangential force component. So these are the three force components which we want to resolve, which we need to find a relationship between. So as we have done in the previous gears, we will consider this tangential force as the base and will express the radial force and axial force in terms of the tangential force. That's what we are doing. So we'll start with the net force P and we'll resolve that force first into PT and PS, and PS will resolve into PA and PR. So everything will get expressed in terms of P, and then we can take ratio and find out the relationship between the different forces. So those relations are given here in design data book. We'll quickly derive them now. Okay, so let's start deriving them. So it will help me in doing that. So first thing is PT. So PT is this force. You want to express that in terms of the net force, which is P. So all the forces will express first in terms of P, and then we will take ratio to express everything in terms of PT. So this red line is PT. So if you take plane ABCD, you have this as, sorry, this has the net force, which is P, which makes an angle, pressure angle alpha with respect to the tangential plane. So the P has to be resolved into two components, PS and PT. So I've written here the first expression for, so what is PT in terms of capital P and PS in terms of capital P. So this is known as, called as a sliding force. And the first one we already know, so that is the tangential force. So tell me what is the relation between P and PT.
P cos alpha.
So PT equal to P into cos of alpha. So alpha is the pressure angle and PS would be
P sin alpha.
P sin alpha. Thanks. So now we have to resolve. So now we got this angle PS, which we want to resolve into. So now we are looking into this particular figure. So we are talking about the plane what is shown there. So in this plane, we are having the PS value we have determined in terms of P. Now we have to resolve that into two components. One is the radial component and another is the axial component. So tell me what is the radial component, what is the axial force component.
P sin alpha cos gamma, PR.
PR is P cos, can you repeat?
Sine alpha cos gamma.
P sine alpha, so that is nothing but PS. So this is PS multiplied by cos of
Gamma.
gamma, where gamma is the pitch cone angle. So that is, this angle is gamma, which is the front cone angle, and the same would be true for the angle between these two. So that is also equal to the gamma. Okay, so that is the expression for PR. And what is the expression for PA? So this is PR. And now we want to know the expression for PA. So what would be the expression?
P sine alpha sine gamma.
P sine alpha sine of gamma. So we got all the expressions in terms of P. So we can express now all the forces in terms of PT. So by taking the ratios, we get PR by PT equal to sine alpha cos gamma divided by cos of alpha. So this implies PR equal to PT multiplied by tan alpha cos gamma, and we are having PA by PT equal to sine alpha sine gamma divided by cos alpha. So it implies that PA equal to PT multiplied by tan alpha sine of gamma. Okay, so these are the expressions you will find in the design data book. So what expressions we derived, those same are given in this particular case. The tangential force is determined by our regular torque divided by mean radius of the bevel gear. So bevel gear tooth. So as we know that pitch circle radius varies from top end to the that is a large end to the small end. So for the purpose, we are considering all the forces to be concentrated at the midpoint of the tooth, which is having the radius which is given by Rm. So the radius at this particular location is Rm. So that Rm also needs to be calculated. So Rm can be calculated in terms of the dimensions. So Rm is the mean radius of the pitch cone. So that can be given as dp by 2 minus b by 2 sine of gamma, where b is the face width. So this is the dimension b. So you can quickly, means you can also derive it. It is just based on the trigonometry, and it can be derived. So it is nothing but, if this is your bevel gear, then this is the face width b, and this is the angle, pitch cone angle gamma, and this particular diameter is dp. So what we are trying to find out is this particular diameter. So it can be calculated by calculating dp by 2 minus height of this triangle. So which can be expressed in terms of b by 2, since this dimension would be equal to b by 2. So that is what this term comes here. Okay, so let's take, okay, now the force analysis doesn't complete with the magnitude. It also need to have the directions to be decided. So the direction of the radial and tangential are similar to that of the spur gear, only the axial force component needs to be, direction of the axial force needs to be understood properly. I'm just trying the two gears which are acting there. So let's consider first, let's decide the direction of motion. So let's say this gear is moving this direction, so the other gear automatically becomes the other direction. Okay, so we are talking about the forces at the midpoint. So let's first decide the tangential force for this particular gear. So tangential force, the logic remains same. The tangential force is for driving gear, it is opposite to that of motion, and for driven gear, it is towards the direction of motion. So let me call this as the driving gear. So the notation which are used for denoting vectors which are perpendicular to the plane of paper is a dot which is coming out of paper or plane or slide, whatever you call, and symbol. This symbol is used for getting inside paper. So we will use that to denote the forces which are acting on these two axes. So for driving gear, can somebody tell me what is the direction of tangential force? Will it be coming out of the paper or it will be going into the paper? So this force, will it come out of the paper or it will go inside the paper?
Out of paper.
Out of paper, because this particular, that's right, Jay. So the driving gear is the motion, the way it is shown, the teeth is moving inside the paper. So teeth is trying to go inside the paper at this means every moment. So the force will be opposite to that. So this would be coming out of the paper. And for the driving gear, the direction of the force would be in the direction of motion. So here it is again, this particular teeth of the driven gear is also moving inside the paper. So the force also will be also along the direction of motion. So the symbol here would be the cross symbol. And here it will be the dot symbol. Okay, so that these are the tangential forces. PT, and this is, so this is PT for pinion, and this is PT for gear. Okay, now we'll talk about the radial force. So radial force, again, the direction logic is same. That is, the radial force is always towards the center. So PR for the gear, let me use another color. So PR for the pinion as well as gear. So this is PR for pinion and this is PR for gear. They will always act towards the center. So this is the PR for gear. And now let's talk about the axial force, which is important. In the sense, axial force is the one which requires some understanding. So the axial force, there are two ways of finding out the direction of axial force. The one way or one guideline is that the axial force acts in such a direction so as to separate the two tooth away from each other. And the other way is by looking at the force equilibrium. So if you look here, the axial force acts in this particular direction. For the gear I'm talking about now. So axial force is in the direction which I have shown. So there are two possibilities. One is this one and another is the other one. Now if you look at this particular diagram, means for the equilibrium of these two bodies, you already have a force in vertical direction which is defined by radial force P. So to nullify this particular force to make the equilibrium, the axial force on gear has to be in this particular direction. So this is the PA for gear. So this particular other direction is not possible because that will match with this direction. So this particular direction is not possible because it will not be able to nullify the radial force. So that is, so this is the P axial for gear, and in similar fashion, the axial force which is acting on the driving gear will be opposite to that of PRG. So this is the P, let me draw it other way so that becomes, so this is P axial for the pinion. So note that the directions what we evolved by the equilibrium directions of the forces, they also match with the first guideline which I told, that the axial force always acts in the direction so as to separate the teeth from each other. So if you look at these two directions, the one which is here and here, you'll find that it will tend to separate the teeth from each other. So they'll try to open up the connection between the two bevel gears. So the either of the way you can use to determine the direction of the force, axial force or thrust force acting on the bevel gears. Now what calculations we did, the formulae that we derived here, they are the forces which are acting on the pinion. Or one can do for gear also. Let's say that we have done these calculations based on the pinion side. Now the forces on the gear, they are written in terms of the forces which we established in for the pinion. So we are having P tangential force for gear, P tangential, P radial for gear, and P axial for gear. So what we established earlier were the forces for the pinion. Now by force equilibrium, we have to write the expressions for the gear. So look at the diagram which we just now draw for the direction of the forces or the direction of the forces acting on the gears. So P tangential on the gear will be equal to P tangential on the pinion. So they will be equal but in opposite direction. So that is the only thing. Now tell me what will be the value of radial force on the gear in terms of the forces which are acting on the pinion.
Of the axial of the pinion.
P axial of the pinion, that's right. So if you note here, what we are trying to do is P radial for the gear. So this is what we are trying to find out. So that must be equal and opposite to that of P axial of the pinion. So that is what we have written here. So if you use the sign, it will be again negative. And similarly, P axial for the gear will be equal to P radial for the pinion with negative sign. So that is how you determine the forces acting on the pinion and gear. So this particular force analysis is 2 points to be remembered, is that these forces are calculated at the midpoint of the tooth width. Why I'm emphasizing that is because later on when we are doing strength calculations, the location used is something else. So remember that force analysis is used to calculate the reactions on the bearings on which these gears are supported. So in order to calculate those bearing reactions, we use the force which is concentrated at the midpoint of the gear tooth. Okay, so that one point you remember. The second point to be remembered is how we determine the direction of the thrust force. The tangential and radial are similar to the earlier gear analysis. The thrust force directions are determined in such a manner so that these two forces try to open up the assembly of the two gears. So that is second point to be remembered. And third point to be remembered is that we calculate all the three force component for the pinion or the smaller gear and the forces on the larger gear are calculated by equilibrium of the forces. So you don't use the same formula for the gear. We first calculate for the smaller gear, and then we use the equilibrium equations to calculate the forces which are acting on the gear. So these are the 3 points that I want you to remember. Now, just take some time to assimilate this, or if you have any question, then you can ask me.
Hello, sir.
Yeah, Jit.
Yes, sir. Sir, my question is that if we have three gears, uh, the
Right.
okay on the right hand side, similar to, so will the middle gear have PTG1 and PTG2? Because PTG1 will act on the left and PTG2 will obviously act on the right hand side. So,
Right.
do
Right.
we add that and then do the calculation, or do we have individual calculation on the left hand side and individual calculation on the right hand side?
No, there will be individual calculation on the left hand side to calculate PTG, let's say PTG1 for the first pair, and on other side there is another gear. That's what you are saying. So here you will get another force component which I called as PTG2 coming from this side. So when you are designing the shaft and the bearings which are supporting this particular shaft, the reactions coming on this bearing will be addition of these two forces. Means vector addition of these two forces.
Okay, sir. Okay, sure. Thank you.
And just since you have put up this point, note that this particular gear is driven as far as this pair is concerned. And as far as this particular pair is concerned, this is a driving gear. So here the force direction is going inside the paper, whereas here the force direction is coming out of the paper. Sorry. So at this point it will come out, at this point it will go in, as far as this middle gear is concerned. Okay, anything else? Okay, so let's take one numerical problem which will illustrate this particular case. Oh, we have some quiz also. Okay, so I think without figure, I think some of you will have a problem in visualizing. That's why the rate of response is slow. See the answer. Okay, so option 2, which is the correct answer. So the thrust force or the axial force is equal and opposite to that of the radial force of the mating gear. So that's what we saw just now. That the radial force on pinion is equal and opposite to that of the axial force. Okay, what is the question? Thrust force on pinion. So thrust force on pinion, that is this particular component, is equal and opposite to radial force on the gear. Direction wise as well as magnitude wise, they are equal.
Sir, I had a doubt.
Yeah,
So it's like the equilibrium thing that we did for the mating gear, like
right.
uh, why is that then specifically? Like we don't do that for the spur gears or for any other type of gears, right?
For other gears, the forces, the axial forces on both the gears are along the same line. They are collinear. Whereas that is not, the radial force of pinion is perpendicular to the radial force of gear. So we cannot, in other cases, we have PR vector, which is parallel to, means PR of pinion is parallel to PR of gear. So they are parallel to each other. Whereas in the case of bevel gears, the radial force direction of one gear is perpendicular to the radial force direction of the other gear. So we cannot have PR correlation. So we have to have the other direction. Means the coordinate system for both the gears are perpendicular to each other. Unlike the other, that is a bevel gear or spur gear, the coordinate axis, the radial direction of both the gears are same. In this case, the radial directions are perpendicular to each other. That's why you cannot equate radial force equal to radial force.
Right, all right, sir. Understood.
Yeah. Okay, so let's move ahead. Okay, so this is a pair of bevel gears transmitting 8 kilowatt at 400 RPM. So you can calculate the torque. The pressure angle is given. So alpha is given. Determine the gear tooth forces. Okay, the face width is given as 40 millimeters. The pitch circle, the large diameter, the pitch circle diameter at the large end is given as 180 and other one is 240. Okay, so let's solve this particular case. Let me copy this figure so that we can. So that while solving we have reference. Okay, so that is the data which is available. So I will start with calculation of the torque, which will require to calculate the tangential force. So the power is given is 8 kilowatt. So 18 to 10 to power 6 divided by 2 pi to RPM divided by 60. So that is 190986 Newton mm. Next, for the purpose of calculations, so let me write down. Let's have the design data book formula in front of us so that we don't keep on shifting. Okay. So we require the pitch cone angle of the pinion. So this gamma angle is required. So tan gamma would be given as Zg divided by Zp. So here the number of teeth are not available to us. So we have to go. So since if you multiply this by module both sides, we'll get it is dg by dp. So that is equal to 180 divided by 2.
It should be ZP by ZG.
Yeah, it should be Zp. Thanks. Sorry. Zp by Zg. So it is 180 divided by 240. So this implies gamma is 36.9 degrees. Next, in order to the force calculation, let me go to the force calculation page. We have determined gamma. We already have been given alpha. We require for calculating torque, we require the value of Rm. So Rm needs to be calculated. So Rm is given as dp by 2 minus p by 2 sine of gamma. I believe that equation is given somewhere. So it is here. So this is the Rm equation. So by substituting the values, we get it as 180 divided by 2 minus 40 divided by 2 into sine of 36.9 degrees. So we get Rn as 78.0 millimeters. So now we can calculate the forces. So Pt equal to mt divided by Rn. So that is 19986 divided by 78. 24,000 2448.5 newtons. So that is the value of Pt. And now we can calculate the PR and PA in terms of Pt and other parameters. So we get PR equal to Pt tan alpha cos gamma 2448.5 into tan of pressure angle, that is 20 degree, into tan of into cos of 36.9 degrees. So this answer is 712.7 newtons. And P actual would be Pt tan alpha sine gamma. So if we calculate that, that will come as 535.1 Newton. So these are the magnitude calculations. Now let's look at the directions of these forces. So let's establish the directions of the forces. Here we are having pinion. Then we are having the gear. Okay, so let's put the forces. So first we'll put PT force. So the motion direction is given as the pinion is moving in this direction. The other one is moving other direction. Let's see which is driving, which is driven. Okay, so pinion is getting the power. So that is the driving. So this is driving gear. Okay, so tangential force is perpendicular to the paper. So whether it is comes out or goes in, that is what we have to decide. So on the pinion, whether the tangential force will come out of the paper or it will go into the paper. I think the design data book figure is matching with our problem, so you don't have to think. Can somebody tell the tangential force for pinion will come out of the paper or it will go into the paper?
Out of the paper.
It will be out of the paper to oppose the motion. So the tangential force would be 2448.5, which comes out, and for the gear it will go into. So this is 2448.5. Now let's establish the directions of the radial and so radial force for the pinion. So that is 712.7 acts in this direction, and the radial force for the gear would be, okay, let's so direction of the radial force is determined here. Now let's calculate the uh, radial force acting on the gear. So we know the direction of radial force acting on the gear. Only this magnitude you'll have to tell me. This magnitude is not same as this magnitude. What would be the magnitude of the radial force on the gear?
535.1.
535.1. That's right. Because that has to be opposite to that of the axial force acting on the pinion. So this will be equal to, means magnitude wise, it will be equal to P axial of the pinion, which we have calculated here. Note that we did this calculation for pinion, means considering the smaller diameter. So that is 535.1, and it will act towards the center. So radial force always towards the center. Only note that the magnitude is not this magnitude. So radial force is something which you have to do. Now the remaining part is relatively simple. Means once you understood this concept, the other part is simple. So let's establish the axial force which is acting on the driving on the pinion. So axial force would be acting in this particular plane. So it can be either direction 1 or it can be direction 2. So can you tell the axial force will be in on the pinion? Will it be in one direction or two direction?
So two direction.
Okay, why Shreyas?
So because it needs to cancel out the PR on the gear.
That's right. So this force has to be opposite to the other force on the other side. So that is why it should be in the other direction. So this and magnitude we have already calculated. So that is equal to 535.1. And what remains is the axial force on the gear. So here again, let me ask once more. So let me call this as direction 1 and direction 2. So what would be the direction of axial force on gear? Will it be direction 1 or it will be direction 2?
So direction 1.
Direction 1 because it has to be opposite to that of the other force on the other gear. So direction
Yes,
1
sir.
is the correct force. And the magnitude must be, direction should be opposite and magnitude also should be this much. So it will be 712.7. Okay, so I hope this force analysis is a bit tricky in case of bevel gears. Specifically for pinion, you can calculate magnitude, but for establishing direction, you must take into account the force directions on the other gear, mating gear.
Hello, sir.
Yeah.
Sir, I'm getting a little confused with respect to the force coming in and going out of the paper. Can you explain that concept once again, please?
Yeah. So what we are doing here is it will be better, more clear if you make it. Okay, so this is the gear, and these are the tooth that we are talking about. So this particular gear, in this particular gear I'm drawing here, so it is revolving in this particular direction. So since this is a driving gear, the tangential force acting on this particular tooth will be opposite to that of the this motion. So this particular tooth is trying to move in this particular direction. So the tangential force would be acting opposite to that. So tangential force will be acting in this particular direction. So if you, what we are doing in the screen is we are looking in this particular direction. So this is the viewpoint, view direction. So for the viewer, the force is coming towards the viewer or out of the paper. So that is what we are drawn here. So this symbol, dot symbol, is for out of paper. Out of paper.
Okay, sir. Okay. Got it. Thank you so much.
Sure. Okay, so now let's enter. So we have done the force analysis. Again, I'm emphasizing that forces are calculated at the midpoint. Now the next topic that we are discussing is the strength of the bevel gear tooth. As we know, in the spur gear and helical gear, the strength of the gear is expressed in terms of tangential force acting on the gear. So note that the tangential force that we did in the force analysis, what we did just now, is used to calculate the reactions on the bearings or the shaft calculation, the load coming on the shaft and so on. They are not used for the uh, tooth force calculation or tooth strength calculation. Why it is so, we'll come to know when we derive that particular expression. So next we'll be developing the expression for the beam strength or the bending strength of the bevel gear. So the expression for that is as given in this particular formula. We'll derive this particular formula. Okay, so let's proceed. So let me explain what this figure is. So in this figure, as we have seen earlier, that the tooth dimensions, they keep on changing as you move from small end to the large end. So what we have considered here is one slice of the tooth having width equal to dx, and the profile would be the involute profile, means in the third dimension it will have the involute profile. What the logic by which we are going to develop this beam strength is as follows. We will use the spur gear formula, that is a Lewis formula for the spur gear, to calculate the beam strength of this small slice. So this small slice, when it is projected on the formative plane, it will be spur gear. So we can use the Lewis formula directly for this slice. So we know what is the maximum bending load what is the maximum tangential force this particular slice can take. And then we will similarly calculate the capacity, tangential force carrying capacity of the individual slices. And rather than adding the forces, what we are going to do is this particular slice can take certain force. Let's call that force as dF. So if you multiply that force by the radius at which it is acting, that is Rx, so that will give us the elemental torque that this particular gear can, this particular slice can withstand. I'll repeat once more. For this slice, I will calculate using Lewis formula what is the maximum tangential force this slice can take. If I multiply that tangential force by the radius at which that force is acting, that is that is given by Rx, that is the pitch circle radius of that particular slice, it will give us the elemental torque, that is the component of the total torque that this particular slice can take. And if you integrate this from over the x, so x here is in this particular direction, x running from the smaller side to the larger side. If you integrate that, you will have the total torque which this particular gear has to transmit. So this part is known to us. That is from power and RPM we know what is the total torque that this teeth has to withstand. And this teeth, this particular MT can be calculated by using this integration of the elemental force which is calculated for this slice multiplied by radius of that particular slice, is the mean pitch circle radius of that particular slice, and we'll integrate it from the over the width of the gear. So that is the outline of the derivation, and we'll now go step by step so that it becomes clear. Okay, so let me start with the derivation. Okay, so when we are talking about this particular slice, we'll apply the Lewis formula. Lewis formula is same as the spur gear bending formula. The elemental force that this slice can carry will be given as, note that the module for this slice will be different. So every slice will have different module because module is given as diameter divided by number of teeth. So every slice will have same number of teeth, but the diameter, pitch circle diameter is different. So that's why I've written mx. So the module is a function of x, where x is given by this particular dimension multiplied by width of that particular slice. So width of that slice would be equal to dx. I'm writing the Lewis formula as we have learned it, multiplied by the bending strength of the gear, which will be UTS by 3. We approximate it by the UTS by 3, and multiplied by the Lewis form factor for this particular gear. So that is what we are doing here. So this Y is based on virtual number of teeth. So Z dash equal to Z divided by cos of gamma. So note that although the module and other dimensions are changing, this virtual number of teeth would remain same for all these slices. So the same form. So this Y is not a function of X. So Y is independent of X, whereas the width, okay, Bx is also not function of X, but Mx is a function of X. So that is what we have to write. So now we have to determine what is the value of Mx in terms of X. So we know the module at the large end. So we want to express this Mx in terms of the module which is defined at the large end. By convention, the module is always defined at the large end. So we have to determine for intermediate slices what is the module in terms of that particular value. So from figure, we get Rx by R would be equal to X by A naught. So by similarity of the triangle, so we have one triangle which is this one, and the other triangle which is this one. So for these two similar triangles, Rx by R vertical heights will be equal to the ratio of their hypotenuse. So that is, for red triangle it is X, for the other triangle it is A naught. Okay, so we get Rx in terms of X. So it is X multiplied by R divided by A naught. Okay, so at the elemental section, the mx is, the module will be defined as pitch circle diameter divided by the number of teeth. So that is, pitch circle diameter will be given as 2 times Rx. So this is the diameter divided by the number of teeth. So that is Z. So if you substitute the Rx, it will be 2x R divided by Z times A naught. And at large end of section, so that is where the model is, means model for bevel gear is always defined at the large end. So that is 2R divided by Z. So this is equation 1, this is equation 2. What we are trying to do is we are trying to express mx in terms of m. So that is what we are doing here. So from 1 and 2, we get mx equal to m times x by a naught. So it means, it physically means that mx is linearly varying with respect to x. So this is equation number 3. And coming back to the Lewis formula, this bx is the width of your gear tooth. So this particular slice has got width of dx. So bx is equal to dx for elemental slice. Bx is equal to dx. Width of this slice is equal to dx. So coming back to our original formula. So dsb, that is the bending strength of the gear or maximum tangential force this slice can take, would be given by this equation. So equal to m sigma b capital Y x into dx divided by a naught. So what I have substituted is, instead of mx, I am writing this m into x by a naught. So this x by a naught is coming here. And instead of bx, I am writing dx. So that is the expression we got. So now the elemental torque. So we got the maximum force that this slice can take. Now we'll find out how much maximum torque this particular slice can take. So elemental torque dmt would be equal to Rx multiplied by d of SB. So we get elemental torque would be equal to Rx is xr by a naught multiplied by the elemental bending strength. So that is m sigma b y x into dx divided by a naught. So the total torque, which is known to us, would be given as integration of this particular quantity. So this quantity can be written m sigma b y r divided by a naught square multiplied by x square dx. And the limits of this particular integration will be across small end to the large end of the width. So we are integrating from this point to this point. So x equal to a naught minus b. So this distance is a naught minus b. And so that is the x value at the small end, and x value at this point is equal to a naught. So between these two limits, we will be integrating. So it is a naught minus b to a naught. That is the limits of the integration. Okay, so after this it is the calculus part. So m sigma b y r a naught square. So x square will be x cubed by 3 a naught and a naught minus b. So this would be equal to m sigma b y r a naught square in the bracket a naught cubed by 3 minus, so it will be a naught minus b the whole cube by 3. So a naught minus b whole cube can be written as a naught cube minus 3 a naught square b plus 3 a naught b square minus b cube divided by 3. So this is nothing but a naught minus b the whole cube. So if we simplify this, it will come out to be m into sigma b into y into r in bracket 1 minus b by a naught plus b square by 3 a naught square. So that is the torque which this particular gear can, the torque which the entire tooth can withstand is given by this particular formula. Now, since per gear, helical gear, we always express the bending strength in terms of force. So we have to find out, we have to convert this torque into the force part. So note here that this torque is converted into force not at the midpoint of the tooth like we did in the force analysis. In force analysis, we calculated the forces to be concentrated at the midpoint of the tooth. Here, for the strength calculation, we are in line with the other dimensions. Since the dimensions are always known at the large end, we assume the force to be concentrated at the large end in order to establish the beam strength equation for the bevel gear. So this empty or the bending strength of the bevel gear is computed at large end of the gear. So bending strength is nothing but a maximum force that tooth can take. Now we have calculated maximum torque which the tooth can take. So the force can be calculated then at any of the location of the tooth. So keeping in line with the other geometric dimensions which are defined at the large end, this force is also calculated at the large end. So this implies that MT will be equal to SB, which is what we are trying to find out, how much maximum force this tooth can take multiplied by R. So R is the large end radius. So this is nothing but dp by 2. Okay, so we'll use that particular expression. So we'll substitute this into MT. So this R gets cancelled with this R, and we get the expression for SB as m sigma b, okay, m into I think I forgot here. Here there is b value is there. The b is taken out from these inner expressions, so there is a b value coming here. So just if you're noting down, just insert B there, into sigma B into Y in the bracket 1 minus B by A naught plus B square by 3 A naught square. Now, usually the face width of bevel gear is taken to be smaller than A naught by 3. So whatever is the slant height, A naught is the, if this is your bevel gear, this is B, and this entire slant width is A naught. So B is kept smaller than A naught. So which means that this particular term will be smaller than 1 by 27. So it is a small number compared to this number. This number will be very small. So this particular term is ignored in the final formula for the calculation, because the practically the proportions of the face width, they will not be larger than A naught by 3. If you give very large face width, you will not get the proper uniform contact over the entire width of the gear. Oh, we have crossed our time limit, so I will just conclude. So with this eliminated, we get the beam strength of the gear as mb sigma by into 1 minus b by A naught. So that is a beam strength of gear, and this particular factor is called as a bevel factor. Bevel factor comes because of the inclination of the gear tooth with respect to the other cases. And note that this is at large end. So force analysis, whatever PT you are getting, that should not be compared with the SB value that we are getting here. You have to calculate force at the large end and then compare with respect to this. Okay, so that's what we will do. Means we'll conclude at this time. And in the next class, we'll calculate the wear strength and take one numerical problem based on that. Okay, so I'm stopping the lecture now.